All right, we're going to look at mathematical induction. Some sequences can be neither arithmetic nor geometric, so we've talked about those two sequences before. Therefore, we don't have a formula readily available to evaluate the sum of the first n terms. So if you're adding an arithmetic sequence or a geometric sequence, there's actually formulas that you can have to add the first number of terms, like if you want to add the first 100 terms or something like that. So we might consider evaluating the nth partial sum for several values of n to find some pattern. So for example, Sn is saying to find the sum of n terms. And so our sequence, you can see it goes 1, 2, 3, 4, 5, all the way to n. So S1 is saying our first sum, which is kind of boring, it's really just the first term. S2 is our second sum, which adds the first term and the second term. And then S3 would be adding the first term, the second term, and the third term together. And so our answer to these is going to be a number where you actually add all those terms together. S4 adds the first 4 terms together, and so you get a 10. And so it says we speculate that Sn, so someone would have to tell you, let's guess that this would be a formula for the sum. So it's just a little guess. So we check and see if this happens for the first couple terms, because we already found the sums by physically adding those terms, but let's see if the formula works. So S1, it's saying that we're going to plug in to this formula a 1 here and a 1 here. So that would become 1 times 1 plus 1 over 2, which does equal 1. Then we're going to plug in to find S2, 2's in those places. So you can see we replace those with 2's. So this would be 2 times 3 over 2, which equals 3. So that works. S3, they plug 3 into those places. So that's 3 times 4 over 2, which is 12 over 2, which is 6. So that worked. So how do we prove that this is going to work all the time? It worked for the first 3, but how do we prove it works all the time? So there's a principle of mathematical induction, and what it says is that if you have a statement involving integers and k is some arbitrary, some random number, if your statement is true for the very first guy, and if you assume it's true for some random guy and can show that it implies the next guy is true, you've proved the statement. So the idea is like dominoes, right? If the first domino falls, as long as you set it up nicely, as long as the first domino falls, if any domino falls, you know the next domino will fall. So you know then that all the dominoes would fall. That's the idea behind mathematical induction. So we want to, again, show that it's true for the first one. It's like you knock down the very first domino. You show that some other random domino was knocked down, or you assume that it did get knocked down. Then you show that the next one can get knocked down. So let's see what that looks like with an example. So for number 1, we want to use mathematical induction to prove that statement. So we're going to actually prove what we kind of came up with. So this was our expression for this nth sum. So to show P1 is true, we want to show that when you plug a 1 in, when n equals 1, this is a true statement. So if n equals 1, we're going to get 1 times 1 plus 1 over 2. And that is equal to 1 times 2 over 2, which is 1. So using the formula, we got 1. But on the left side, we know that the sum of the first guy is 1. So we've showed that it's true for P1. So if we want to assume PK is true, we're going to assume that the sum of all the numbers up to k does equal, I'm going to plug in k's, so that's just showing me that this is some random number. So I'm going to assume that that is true. So what we want to show is that the next guy is true. We want to show that the k plus 1 is true. And so the k plus 1 means I'm going to add all the numbers all the way up to k plus one more term. So one more term would be found by looking at k plus 1. And so we want to show, we're not sure, but we want this to be equal to, if I put k plus 1 in, so k plus 1 over 2. So we don't know, that's why I put a little question mark on there. So let's see what's happening on the left side. Well, 1 plus 2 all the way to k, we already have assumed that that's equal to k times k plus 1 over 2. So then we're going to add to that k plus 1. Now, in order to actually add these chunks together, we need to have a common denominator. So this is over 1, so I'm going to multiply by 2 by 2. So this is going to be k times k plus 1 plus, this will be 2k plus 2 all over 2. So we want this to look like that top numerator to prove that it's true, which I realize I just missed out on putting a 1 here. That was k plus 1. So let's simplify the top here of our left side and see what that looks like. If I distribute, that's going to be k squared plus k plus 2k plus 2 over 2. Or in other words, k squared plus 3k plus 2 over 2. Let's look at what's going on the right side. The right side is actually k plus 2 here. So if I distribute, I'm going to get k squared plus 2k plus 1k plus 2. And so you can see that this is exactly what we got over here. This is k squared plus 3k plus 2. So we were able to show that the left side does equal the right side. So we just showed that if we can assume k plus 1 is true, or k is true, then we have just showed that the k plus 1 is true. All right, let's try that again. So number 2. So our statement right now is if we add 2 plus 6 plus 10 plus all the way to the nth term, that's equal to 2n squared. Now this is just an arithmetic sequence. It's just adding 4 every time. And so this last term, 4n minus 2, that's the nth term. That's just a way to show you how it's finding those terms. So to show P1 is true, we're going to look at n equal to 1, which would mean on the left, we just have the 2, and we want to show that that's equal to if I put a 1 into the formula on the right side. So let's see, we're not sure, but we wanted 2 times 1 squared. Well, that is 2, so we showed that 2 equals 2. So the first term is true. That's like the first domino was pushed. So we want to assume pk is true. So if n equals k, that's 2 plus 6 plus 10 plus plus 4k minus 2 does equal 2k squared. We're going to assume this is true. And so if this is true, we want to show that the k plus 1 is true. That n equals k plus 1 is true. And so what that statement would look like is 2 plus 6 plus 10 plus plus that 4k minus 2, but then we want the k plus 1 term. So that would be 4 times k plus 1 minus 2. And that's supposed to equal 2 times k plus 1 squared. So what we have, this is what we want to show. We're not totally sure that it will equal that right side, but what we do know from our assumption is that these first guys right here is 2k squared. So what does it simplify to be if I take 2k squared plus this extra term, 4 times k plus 1 minus 2? Well, if I distribute, that's going to be 4k plus 4. I have 2k squared over here minus 2. So I have 2k squared plus 4k plus 2. That would simplify. So this is what the left-hand side is. So let's look at what's going on the right side, because maybe you know how to factor, maybe you don't. If I just simplify this by multiplying k plus 1 squared, that's k plus 1 times k plus 1, distribute, we end up with k squared plus 1k plus 1k plus 1, and then 2 times that. Well, this is 2k. So this will be 2k squared plus the 4k plus 2. It does work. They are equal. So we just showed that the k plus 1 is true, which means that this statement is true. So we have proved it. And that's mathematical induction.